We start Chapter 7 on Newton's third law. When a hammer hits a nail, it exerts a forward force on the nail. But at the same time, the nail exerts a backward force on the hammer. There's the force of the hammer on the nail. There's the force of the nail on the hammer. If you don't believe it, imagine that you were hitting the nail with a glass hammer. It's the force of the nail on the hammer that would cause the glass to shatter. Other interacting objects include a bat hitting a ball. At the same time, the ball exerts a force on the bat. When you pull someone with a rope in a tug of war, that person pulls back on you. When your chair pushes up on you, the normal force, you are pushing down on the chair. It turns out that all forces come in pairs, and you can call these action-reaction pairs. The forces occur simultaneously, and we cannot say which one is the action and which one is the reaction. Example, object A exerts a force on object B, then object B exerts a force on object A. And this pair of forces is called an action-reaction pair. Here's object A, here's object B. Here's force A on B, this vector. Here is force B on A, is this vector. Long-range forces, such as gravity, also come in pairs. If you release a ball, it falls because the Earth's gravity exerts a downward force, F, Earth on ball. But at the same time, the ball pulls upward on the Earth with a force, F, ball on Earth. And here's you can see the ocean tides are an indication of the long-range gravitational interaction between Earth and Moon. So the Earth pulls on the Moon, which causes the Moon to orbit the Earth. The Moon also pulls on the Earth, which is one of the things that causes these tidal bulges. So back in chapters 5 and 6, we always considered forces acting on a single object. So maybe isolated object A, we used the forces, found the net force, and we could find the acceleration of this object as the net force divided by the mass. In this chapter, we extend this particle model to include more than two objects, two or more objects. Here's three objects that are interacting, A, B, and C, and each line represents some sort of an interaction of an action-reaction pair of forces. And we can give them the labels F, A on B is the force of A on B, and F, B on A, the force of B on A. Example, what if A is the hammer, B is the nail, and C is the earth? The earth interacts with both the hammer and the nail via gravity. So there's these two lines right there. But the earth is remaining at rest while the hammer and the nail move. We're interested in analyzing the hammer and the nail, so we define the system as those objects whose motion we want to analyze. And the environment is objects external to the system. So we can draw a little box around this in an interaction diagram. Okay? The hammer and the nail are our system, and the earth is the environment. So interactions with the environment, like the fact that both the hammer and the nail are pulled down, are called external forces. So how do things move? For example, you've got this sprinter guy here. What force, what outside force on this man causes him to accelerate? Well, think about walking. If you were to walk on a very, very slippery floor and you wanted to walk forward, your foot would slip and slide backward. In order to walk properly, your foot must stick to the floor as you straighten your leg and move your body forward. So what's the sticking force that's preventing your shoe from slipping? It's static friction. The static friction force points in the forward direction on you. So it's actually static friction that propels you forward. Here's a picture of a person pushing backwards on the floor with a force of static friction, and then the earth pushes forward on the person, also with static friction. Here's a car with front-wheel drive. You step on the gas, it tries to rotate this wheel clockwise. The wheel pushes backwards on the earth with a force of static friction. The Earth pushes forwards on the car with a force of static friction, and that is what causes the car to go forward. Here's a rocket which pushes a lot of hot gases backwards. Okay? So the rocket pushes on the gases backwards, the gases push upward on the rocket. That's the thrust force. Okay, Newton's third law can be summed up like this. Every force occurs as one member of an action-reaction pair of forces. These two forces act on different objects, and they are equal in magnitude but opposite in direction. Newton's third law in equation form looks like this. The force of A on B is the negative of the force of B on A, where B and A are different objects. You can describe it with a catchy phrase, which is not as precise, by saying, for every action, there is an equal but opposite reaction. So let's consider a ball which is released and falls towards the Earth. According to Newton's third law, there should be an equal and opposite force pulling upwards on the Earth from the ball. So why don't we notice this? Well, let's use Newton's second law to compute the acceleration of both objects. The acceleration of the ball is the force on the ball divided by the mass of the ball. Now the gravity force in this case turns out to be the mass of the ball times g, where g is 9.8. So if you take the mass of the ball times g divided by the mass of the ball, the masses of the ball cancel on the top and the bottom, and you get the acceleration of the ball as negative g, or negative 9.8 meters per second squared. The acceleration of the Earth is computed the same way, but this time you use Newton's second law for the Earth, so you take the force and divide it by the mass of the Earth. So you end up with g again times the ratio of the mass of the ball to the mass of the Earth, okay, which is about 10 to the 24 kilograms. So if the ball is 1 kilogram, the acceleration of the Earth is about 2 times 10 to the minus 24 meters per second squared. So this isn't even in like a femtometer per second squared. It's extremely small, and no one could ever measure it. Okay, acceleration constraints. Oftentimes you have two objects that are connected somehow, like this tow truck connected to the car, and they move together. So if the tow truck goes forward 1 meter, the car also goes forward 1 meter in the same amount of time. This means they have the same displacement, also the same velocity, and also the same acceleration. And so the acceleration constraint here is that they have equal accelerations. So if we say a sub c is the acceleration of the car, a sub t is the acceleration of the truck, we can say that they're equal, and we can drop the subscripts and just call that a. Here we have two objects that are connected by a string which goes over a pulley, and it's the same sort of thing. If this object B goes down 1 meter, in that same amount of time, object A has to go to the right by 1 meter because they're connected. So the magnitudes of their displacements will be the same, magnitudes of their velocities will be the same, and the magnitudes of their accelerations will be the same. Only thing in this case is if you define positive towards the right and positive to the up, or towards up in the y direction, then these accelerations will have opposite signs. So as A moves in the positive x direction, B moves in the negative y direction, so the acceleration constraint here is the acceleration of A is negative the acceleration of B. Okay, so here's a heavy safe hanging from the ceiling by a rope. And if we look at a magnified view of this rope and we could somehow see all of the atoms are connected by molecular bonds which can be modeled as these little springs. So the combined pulling force of these billions of stretched molecular springs is what creates the tension. And this pulls equally in both directions. If you look at a very thin cross-section of this rope, here in figure B, it's in equilibrium as the safe is just hanging there. So the upwards pull from the bonds above must equal the downward pull from the bonds below. And that's where the tension comes from. Here we have two objects that are connected by a string, and there's a force pulling this object B to the right. So the whole thing will accelerate towards the right. Now if you examine the forces involved at the points where the string is connected to the objects, you've got the tension of the string on A to the right equals tension of A on the string to the left. And here's this tension of object B on the string, which is equal and opposite to the tension of the string on B. But if the string doesn't weigh as much or weighs much less than either of these objects, then these two will be equal. So this is called the massless string approximation. It means that the mass of the string or rope is much less than the masses of the objects that it connects. So we say that the tension of B on S is equal to the tension of A on S. And it acts as if these two forces are an action-reaction pair. So all a massless string does is it transmits a force from A to B without changing the magnitude of that force. And for most of the problems in this course, you just assume that the strings are massless, or if mass isn't given, you just neglect it. This also works with these what are called ideal pulleys. So a pulley that is massless and frictionless. So in other words, its mass is much, much less than the masses of the objects that are connected over the pulley, and also it's not a sticky thing. It's the string slips over it pretty easily. So in this case, the magnitude of the tension on A is equal to the magnitude of the tension on B. So again, you kind of connect these two forces as if they're two members of an action-reaction pair. So here's the free body diagram for mass A. It has the normal force and the force of gravity on it, and the tension from the string. And here's the free body diagram of mass B. It has force of gravity on it, and it has that same tension, or force with the same magnitude of tension as this tension up here. So we can put an as if and kind of connect these two forces as if they're an action-reaction pair, because the tension force just gets turned by the pulley. Section 7.5 is a whole lot of examples. I'd like you to read through those, and then you're done chapter 7.